Okay, last video for now. Let's get a chemistry in. And then I'm going to lay down for a bit. So let's go OpenStax. Leave them on chapter 4. Science. Chemistry. Download. File. That guy. And yep, chapter 4. Close that. Ouch. Ow. Sorry. Ah. Chapter 4. Stoichiometry of chemical reactions. Oops. 175. Ah. Hold on a sec. I'll try something real quick. Okay, sorry. Chapter outline. 4.1, writing and balancing chemical equations. 4.2, classifying chemical reactions. 4.3, reaction stoichiometry. 4.4, reaction yields. 4.5, quantitative chemical analysis. Introduction. Solid fuel rockets are a central feature in the world's space exploration programs, including the new Space Launch System being developed by the National Aeronautics and Space Administration to replace the retired Space Shuttle fleet. The engines of these rockets rely on carefully prepared solid mixtures of chemicals combined in precisely measured amounts. Igniting the mixture initiates a vigorous chemical reaction that rapidly generates large amounts of gaseous products. These gases are ejected from the rocket engine through its nozzle, providing the thrust needed to propel heavy payloads into space. Both the nature of this chemical reaction and the relationships between the amounts of the substances being consumed and produced by this reaction are critically important considerations that determine the success of the technology. This chapter will describe how to symbolize chemical reactions using chemical equations, how to classify some common chemical reactions by identifying patterns of reactivity, and how to determine the quantitative relations between the amounts of substances involved in chemical reactions, that is, the reaction stoichiometry. 4.1, writing and balancing chemical equations. By the end of this section, you'll be able to derive chemical equations from narrative descriptions of chemical reactions, write and balance chemical equations in molecular, total ionic, and net ionic formats. An earlier chapter of this text introduced the use of element symbols to represent the individual atoms. When atoms gain or lose electrons to yield ions, to combine with other atoms to form molecules, their symbols are modified or combined to generate chemical formulas that appropriately represent these species. Extending the symbolism to represent both the identities and the relative quantities of the substance undergoing chemical or physical change involves writing and balancing a chemical equation. Consider, as an example, the reaction between one methane molecule and two diatomic oxygen molecules to produce one carbon dioxide molecule and two water molecules. The chemical equation representing this process is provided in the upper half of figure 4.2, with space-filling molecular models shown in the lower half of the figure. This example illustrates the fundamental aspects of any chemical equation. 1. The substances undergoing reaction are called reactants, and their formulas are placed on the left side of the equation. The substances generated by the reaction are called products, and their formulas are placed on the right side of the equation. Plus signs separate individual reactant and product formulas, and an arrow separates the reactant and product, left and right sides of the equation. The relative numbers of reactant and product species are represented by coefficients. The numbers placed to the left of each formula, a coefficient of 1 is typically omitted. Hold on one sec. I'm going to pause for a minute. All right, I'm going to try to get through this. This is pretty difficult. The itchy. 2. The substances generated by the reaction are called products, and their formulas are placed on the right side of the equation. 3. Plus signs separate. Oh, did that already. 4. The relative numbers of reactants and product species are represented by coefficients. Numbers placed immediately to the left of each formula. A coefficient of 1 is typically omitted. It is common practice to realize the smallest possible whole number coefficients in a relative chemical equation, as is done in this example. Realize, however, that these coefficients represent the relative numbers of reactants and products, and therefore they may be correctly interpreted as ratios. Methane and oxygen reacts to yield carbon dioxide and water in a 1:2 to 1:2 ratio. This ratio is satisfied in the numbers if the numbers of these molecules are respectively 1:2:1:2 or 2:4:2:4 or 3:6:3:6 and so on. Likewise, these coefficients may be interpreted with regard to any amount number unit, and so this equation may be correctly read in many ways, including 1 methane molecule and 2 oxygen molecules react to yield 1 carbon dioxide molecule and 2 water molecules. 1 dozen methane molecules and 2 dozen oxygen molecules react to yield 1 dozen carbon dioxide molecules and 2 dozen water molecules. 1 mole of methane molecules and 2 moles of oxygen molecules react to yield 1 mole of carbon dioxide molecules and 2 moles of water molecules. Okay. Balancing equations. The chemical equation described in section 4.1 is balanced, meaning that equal numbers of atoms for each element involved in the reaction are represented on the reactants and product sides. This is a requirement by the equation, or the equation must satisfy to be consistent with the law of conservation of matter. It may be confirmed by simply summing the numbers of atoms on either side of the arrow and comparing these sums to ensure they are equal. Note that the number of atoms for a given element is calculated by multiplying the coefficient of any formula containing that element by the element's subscript in the formula. If an element appears to be more than one formula on a given side of the equation, the number of atoms represented in each must be computed and then added together. For example, both oxygen species in this example reaction, CO2 and H2O, contain the element oxygen, and so the number of oxygen atoms on the product side of the equation is, and then there's that equation. The equation for the reaction between the methane and oxygen to yield carbon dioxide and water is confirmed to be balanced for this approach, as shown here. Okay. A balanced chemical equation often may be derived from a qualitative description of some chemical reaction by a fairly simple approach known as balancing by inspection. Consider, as an example, the decomposition of water to yield molecular hydrogen and oxygen. This process is represented qualitatively by an unbalanced chemical reaction. Comparing the number of hydrogen and oxygen atoms on either side of this equation confirms its imbalance. The number of H atoms on the reactant and product side of this equation are equal, but the numbers of O atoms are not. To achieve balance, the coefficients of the equation may be changed as needed. Keep in mind, of course, that the formula subscripts define, in part, the identity of the substance, and so these cannot be changed without altering the qualitative meaning of the equation. For example, changing the reactant formula from H2O and H2O2 would yield balance to the number of atoms, but doing so also changes the reactant's identity. It's now hydrogen peroxide and not water. The O atom balance may be achieved by balancing the coefficient for H2O to 2. The H atom balance was upset by this change, but it is easily reestablished by changing the coefficient of H2 product to 2. These coefficients yield equal numbers of both H and O atoms on reactants and product sides, and the balanced equation is therefore 2H2O plus equals 2H2 plus O2. Okay. It is sometimes convenient to use fractions instead of integers as intermediate coefficients in the process of balancing a chemical equation. When balance is achieved, all the equation's coefficients may then be multiplied by a whole number to convert the fractional coefficients to integers without upsetting the atom balance. For example, consider the reaction of ethane with oxygen to yield H2O and CO2. Represented by the unbalanced equation there, following the usual inspection approach, one might first balance C and H atoms by changing the coefficients for the two product species as shown. This results in 7 O atoms on the product side of the equation, an odd number. No integer coefficient can be used with the O2 to react to yield an odd number, so a fractional coefficient 7/2 is used instead to yield a provisional balanced equation. A conventional balanced equation with integer-only coefficients is derived by multiplying each by 2. There you go. Finally, with regard to balanced equations, recall the conventions dictates the use of smallest whole number coefficients. Although the equation between the molecular nitrogen and molecular hydrogen to produce ammonia is indeed balanced, the coefficients are not the smallest possible integers representing the relative numbers of reactants and product molecules. Dividing each coefficient by the greatest common factor, 3, gives the preferred equation there. Additional information in chemical equations. The physical states of reactants and products in chemical equations are very often, included or indicated with a parenthetical abbreviation following the formulas. Common abbreviations include S for solids, L for liquids, G for gases, and AQ for substances dissolved in water. Aqueous solutions are introduced in the preceding chapter. These notations are illustrated in the example equation here. This equation represents the reaction that takes place when sodium metal is placed in water. The solid sodium reacts with liquid water to produce molecular hydrogen gas and the ionic compound sodium hydroxide, a solid in pure form but readily dissolved in water. Special conditions necessary for a reaction are sometimes designated by writing a word or symbol above or below the equation's arrow. For example, a reaction carried out by heating may be indicated by the uppercase Greek letter delta, which is a triangle, over the arrow. For other examples of these special conditions will be encountered in more depth in later chapters. Equations for ionic reactions. Given the abundance of water on Earth, it stands to reason that a great many chemical reactions take place in aqueous media. When ions are involved in these reactions, the chemical equations may be written with various level of detail appropriate to their intended use. To illustrate this, consider a reaction between ionic compounds taking place in an aqueous solution. When aqueous solutions of CaCl2 and AgNO3 are mixed, a reaction takes place producing aqueous calcium nitrate and solid silver chloride. So calcium chloride plus 2 silver nitrates equals calcium nitrate plus 2 silver chlorides. This balanced equation, derived in the usual fashion, is called a molecular equation because it doesn't explicitly represent the ionic species that are present in solution. When ionic compounds dissolve in water, they may dissociate into their constituent ions, which are subsequently dispersed homogeneously throughout the resulting solution. A thorough discussion of this important process is provided in the chapter on solutions. Ionic compounds dissolved in water are, therefore, more realistically represented as dissociated ions in this case, and then it shows them dissociated. Calcium chloride equals the calcium ion and the chloride ions. Silver nitrates equals the silver ions plus the nitrate ions, so on. Unlike these three ionic compounds, silver chloride does not dissolve in water to a significant extent, as signified by its physical state notation solid. Explicitly representing all dissolved ions results in a complete ionic equation, In this particular case, the formulas for the dissolved ionic compounds are replaced by formulas for their dissociated ions. So you have calcium ions, chloride ions, silver ions, nitrate ions. That gives you calcium ions, nitrate ions, and silver chlorides. Examining this equation shows that two chemical species are present in identical form on both sides of the arrow, calcium ion and nitrate ion. These spectator ions, whose presence is required to maintain charge neutrality, are neither chemically nor physically changed by the process, and so they may be eliminated from the equation to yield a more succinct representation called the net ionic equation. And basically what they do is they just eliminate on both sides the same ions that don't form a solid or a liquid or any separated structure. Following the convention of using the smallest possible integers as coefficients, this equation is then written: chloride and silver make silver chloride. This net ionic equation indicates that solid silver chloride may be produced from dissolved chloride and silver 1 ions, regardless of the source of these ions. These molecular and complete ionic equations provide additional information, namely the ionic compounds used as sources of chloride and silver. 4.2, classifying chemical reactions, learning objectives. So by the end of this section, you'll be able to define 3 common types of chemical reactions: precipitation, acid-base, and oxidation reduction. Classify chemical reactions as one of these 3 types given appropriate descriptions or chemical equations. Identify common acids and bases. Predict the solubility of common inorganic compounds by using solubility rules. Compute the oxidation states for elements and compounds. Humans interact with one another in various and complex ways, and we classify these interactions according to a common patterns of behavior. When 2 humans exchange information, we say they are communicating when they exchange blows with their fists or feet. We say that they are fighting. Faced with a wide range of varied interactions between chemical substances, scientists have likewise found, if convenient or even necessary, to classify chemical interactions by identifying common pattern of reactivity. This module will provide an introduction to 3 of the most prevalent types of chemical reactions: precipitation, acid-base, and oxidation reduction. Precipitation reactions and solubility rules. A precipitation reaction is one in which dissolved substances react to form one or more solid products. Many reactions of this type involve the exchange of ions between ionic compounds in aqueous solutions and are sometimes referred to as double displacement, double replacement, or metathesis reactions. These reactions are common in nature and are responsible for the formation of coral reefs in oceans and kidney stones in animals. They are used widely in industry for production of a number of commodity and specialty chemicals. Precipitation reactions also play a central role in many chemical analysis techniques, including spot tests used to identify metal ions and gravimetric methods for determining the composition of matter. See the last module of this chapter. The extent to which a substance may be dissolved in water, or any extent, is quantitatively expressed as its solubility. Defined as the maximum concentration of a substance that can be achieved under specified conditions, substances with relatively large solubilities are said to be soluble. A substance will precipitate when solution conditions are such that its concentration exceeds its solubility. Substances with relatively low solubilities are said to be insoluble, and these are the substances that readily precipitate from solution. More information on these important concepts is provided in a later chapter on solutions. For purposes of predicting the identities of solutions formed by precipitation reactions, one may simply refer to patterns of solubility that have been observed for many ionic compounds. A vivid example of precipitation is observed when solutions of potassium iodide and lead nitrate are mixed, resulting in the formation of solid lead iodide. There's the equation. Notice how the lead is in the 2 form. This observation is consistent with the solubility guidelines. The only insoluble compounds among all those involved is lead iodide, one of the exceptions to the general solubility of iodide salts. The net ionic equation representing this reaction is lead iodide is a bright yellow solid that was formerly used as an artist pigment known as iodine yellow. The properties of pure PbI2 crystals make them useful for fabrication of X-ray and gamma ray detectors. Solubility guidelines in 4.1 may be used to predict whether a precipitation reaction will occur when solutions of soluble ionic compounds are mixed together. One merely needs to identify all the ions present in the solution and then consider if possible cation-anion pairing could result in an insoluble compound. For example, mixing solutions of silver nitrate and sodium chloride will yield a solution containing silver ion, nitrate ion, sodium ion, chloride ions. Aside from the two ionic compounds originally present in the solutions, silver nitrate, sodium chloride, two additional ionic compounds may be derived from this collection of ions, silver nitrate and silver chloride. The solubility guidelines indicate all nitrate salts are soluble, but that AgCl is one of insoluble. A precipitation reaction, therefore, is predicted to occur as described by the following equations. Acid-base reactions. An acid-base reaction is one in which the hydrogen ion, H+, is transferred from one chemical species to another. Such reactions are of central importance to numerous natural and technological processes, ranging from the chemical transformations that take place within cells and the lake and oceans to the industrial scale. Production of fertilizers, pharmaceuticals, and other substances essential to society. The subject of acid-base chemistry, therefore, is worthy of thorough discussion, and a full chapter is devoted to this topic later in the text. For purposes of this brief introduction, we will consider only the more common types of acid-base reactions that take place in aqueous solutions. In this context, an acid is a substance that will dissolve in water to yield hydronium ions, H3O+. As an example, consider the equation below, shown here. The process represented by this equation confirms that hydrogen chloride is an acid. When dissolved in water, H3O+ ions are produced by a chemical reaction in which H+ ions are transferred from HCl molecules to H2O molecules. So basically what's happening is the hydrogen is basically behaving like an electron, almost. It's still considered, well, for HCl, yeah, but for weaker acids, no. It's more of a share. That's interesting. The process represented by this equation confirms that when dissolved in water, H3O+ ions are produced by a chemical reaction in which H+ ions are transferred from HCl molecules to H2O molecules. The nature of HCl is such that its reaction with water, as just described, is essentially 100% efficient. Virtually every HCl molecule that dissolves in water will undergo this reaction. Acids that completely react in this fashion are called strong acids, and HCl is among just a handful of common acid compounds that are classified as strong. A far greater number of compounds behave as weak acids and only partially react with water, leaving a large majority of dissolved molecules in their original form and generating a relatively small amount of hydronium ions. Weak acids are commonly encountered in nature, being the substances partly responsible for the tangy side of citrus fruits, the stinging sensation of insect bites, and the unpleasant smells associated with body odor. A familiar example of a weak acid is acetic acid, the main ingredient in food vinegars. Here's the equation. When dissolved in water under typical conditions, only about 1% of acetic acid molecules are present in the ionized form, CH3CO2-. The use of the double arrow in the equation above denotes a partial reaction aspect of this process, a concept addressed fully in the chapters on chemical equilibrium. A base is a substance that will dissolve in water to yield hydroxide ions. The most common bases are ionic compounds composed of alkali or alkaline earth metal cations, combined with the hydroxide ion, for example. There they are. Unlike the acid compounds discussed previously, These compounds do not react chemically with water. Instead, they dissolve and dissociate, releasing hydroxide ions directly into the solution. For example, KOH and BOH2 dissolve in water and dissociate completely to produce cations, sodium and barium, respectively, and hydroxide ions. These bases, along with other hydroxides that completely dissociate in water, are considered strong bases. Consider, as an example, the dissolution of Li, sodium hydroxide, in water. This equation confirms that sodium hydroxide is a base. When dissolved in water, sodium hydroxide dissociates to yield sodium hydroxide ions. This is also true for any other ionic compound containing hydroxide ions. Since the dissociation process is essentially complete when ionic compounds dissolve in water under typical conditions, sodium hydroxide and other ionic hydroxides are all classified as strong bases. Unlike ionic hydroxide, some compounds produce hydroxide ions when dissolved by chemically reacting with water molecules. In all cases, these compounds react only partially and so are classified as weak bases. These types of compounds are also abundant in nature and important commodities in various technologies. For example, global production of the weak base ammonia is typically well over 100 metric tons annually, being widely used as an agricultural fertilizer, a raw material for chemical synthesis of other compounds, and an active ingredient in household cleaners. When dissolved in water, ammonia reacts partially to yield hydroxide ions, as shown here. This is by definition an acid-base reaction, in this case involving the transfer of H plus ions from the water molecules to the ammonia molecules. Under typical conditions, only about 1% of the dissolved ammonia is present as NH4 plus ions. A neutralization reaction is a specific type of acid-base reaction in which the reactants are an acid and a base, but not water, and the products are often a salt and water. To illustrate a neutralization reaction, consider what happens when a typical antacid, such as milk of magnesia, is ingested to ease symptoms associated with excess stomach acid. There it is. Note that in addition to water, this reaction produces salt and magnesium chloride. Oxidation reduction reactions. Earth's atmosphere contains about 20% molecular oxygen, O2, a chemically reactive gas that plays an essential role in the metabolism of aerobic organisms and in many environmental processes that shape the world. The term oxidation was originally used to describe chemical reactions involving O2, but its meaning has evolved to refer to a broad and important reaction class known as oxidation reduction reactions. A few examples of such reactions will be used to develop a clear picture of this classification. Some redox reactions involve the transfer of electrons between reactant species to yield ionic products, such as the reaction between sodium and chlorine to yield sodium chloride. It is helpful to view the process with regard to each individual reactant, that is, to represent the fate of each reactant in the form of an equation called a half reaction. These equations now show the sodium atoms lose electrons while the chlorine atoms gain electrons. The S subscript for the resulting ions signifying they are present in the form of a solid ionic compound. For redox reactions of this sort, the loss and gain of electrons define the complementary process that occur. Oxidation is the loss of electrons. Reduction is the gain of electrons. In this reaction, then, sodium is oxidized and chlorine undergoes reduction. Viewed from a more active perspective, sodium functions as a reducing agent since it provides electrons to chlorine. Likewise, chlorine functions as an oxidizing agent as it effectively removes electrons from sodium. So the reducing agent is a species that is oxidized, and the oxidizing agent is a species that is reduced. Some redox processes, however, do not involve the transfer of electrons. Consider, for example, the reaction similar to the one yielding NaCl. Okay. Hold on one sec. Ah! Itchy, itchy. Okay. Product of this reaction, some redox processes, right there. The product evolved, shit. The product of this reaction is a covalent compound, so transfer of electrons in the explicit sense is not involved. To clarify, the similarity of this reaction of the previous one and permit an unambiguous definition of redox reactions, a property called oxidation number, has been defined. The oxidation number, or oxidation state, of an element in a compound is the charge its atoms would possess if the compound were ionic. The following guidelines are used to assign oxidation numbers to each element in a molecular ion. 1. The oxidation number of an atom is an elemental substance is 0. 2. The oxidation number of a monatomic ion is equal to the ion's charge. 3. Oxidation numbers for common nonmetals are usually assigned as follows. Hydrogen +1 when combined with nonmetals, -1 when combined with metals. Oxygen -2 in most compounds, sometimes -1, so-called peroxides, O22-, very rarely -1/2, so-called superoxides. Positive values when combined with F values vary. Halogens, -1 for F always, -1 for other halogens except when combined with oxygen or other halogens. Positive oxidation and others, in these cases, varying values. 4. The sum of oxidation numbers for all atoms in a molecule or polyatomic ion equals the charge on the molecular ion. Note, the proper convention of reporting charge is to write the number first, followed by the sign, while oxidation number is written with the reverse sequence, followed by sign, followed by number. This convention aims to emphasize the distinction between the two related properties. Using the oxidation number concept, an all-inclusive definition of redox reaction has been established. Oxidation redox reactions are those in which one or more elements involved undergo a change in oxidation number, while the vast majority of redox reactions involve changes in oxidation number for two or more elements. A few interesting exceptions to this rule do exist. Definitions for the complementary process of this reaction class are correspondingly revised as shown here. Oxidation, increase in oxidation number. Reduction, decrease in oxidation number. Returning to the reactions used to introduce this topic, they may now both be identified as redox processes. In the reaction between sodium and chlorine to yield sodium chloride, sodium is oxidized. Its oxidation number increases from 0 in the sodium to +1 in sodium chloride. The chlorine is reduced. Its oxidation number increases from 0 to chlorine to -1 in sodium chloride. In the reaction between molecular hydrogen and chlorine, hydrogen is oxidized. Its oxidation number increases from 0 in H2 to 1 in HCl, and chlorine is reduced. Its oxidation number decreases from 0 in Cl2 to -1 in HCl. Several subclasses of redox reactions are recognized, including combustion reactions, in which the reductants, also called a fuel, and oxidants, often but not necessarily molecular oxygen, react vigorously and produce significant amounts of heat, and often light, in the form of a flame. Solid rocket fuel reactions, such as the one depicted in Figure 4.1, are combustion processes. A typical propellant reaction in which solid aluminum is oxidized by aluminum perchlorate is represented by the equation there. Single displacement replacement reactions are redox reactions in which an ion or in solution is displaced or replaced via the oxidation of a metallic element. One common example of this type of reaction is the acid oxidation of certain metals. Metallic elements may also be oxidized by solutions of other metal salts. For example, there's an example. This reaction may be observed by placing copper wire in a solution containing a dissolved silver salt. Silver ions in solution are reduced to elemental silver at the surface of the copper wire, and the resulting Cu2+ ions dissolve in the solution to yield a characteristic blue color. Balancing redox reactions via the half reaction method. Redox reactions that take place in aqueous media often involve water, hydronium ions, and hydroxide salts. Sorry. And hydroxide ions as reactants or products. Although these species are not oxidized or reduced, they do participate in chemical change in other ways, e.g., providing elements required to form oxyanions. Equations representing these reactions are sometimes very difficult to balance by inspection, so systematic approaches have been developed to assist in the process. One very useful approach is to use the method of half reactions, which involves the following steps. Write the two half reactions representing the redox process. Balance all elements except oxygen and hydrogen. Balance oxygen atoms by adding H2O molecules. Balance hydrogen atoms by adding H plus ions. 5. Balance charge by adding electrons. If necessary, multiply each half reaction's coefficients by smallest possible integers to yield equal numbers of electrons in each. Add to balance half reactions together and simplify by removing species that appear on both sides of the equation. For reactions occurring in basic media, excess hydroxide ions, carry out these additional steps. Add hydroxide ions to both sides of the equation in equal numbers to the H plus ions. On the side of the equation containing both H plus and OH ions, combine these ions to yield water molecules. Simplify the equation by removing any reductant water molecules. Finally, check to see that both the numbers of atoms and the total charges are balanced. 4.3, reaction stoichiometry. By the end of this section, you'll be able to explain the concept of stoichiometry as it pertains to chemical reactions, use balanced chemical equations to derive stoichiometric factors relating amounts of reactants and products, perform stoichiometric calculations involving mass, moles, and solution molarity. A balanced chemical equation provides a great deal of information in a very succinct format. Chemical formulas provide the identities of the reactants and products involved in the chemical change, allowing classification of the reaction. Coefficients provide the relative numbers of these chemical species, allowing a quantitative assessment of the relationships between the amounts of substances consumed and produced by the reaction. These quantitative relationships are known as the reaction stoichiometry, a term derived from the Greek words stoichion, meaning element, and metron, meaning measure. In this module, the use of balanced chemical equations for various stoichiometric applications is explored. The general approach to using stoichiometric relationships is similar in concept to the way people go about many common activities. Food preparation, for example, offers an appropriate comparison. A recipe for making 8 pancakes calls for 1 cup pancake mix, 3/4 cups of milk, and 1 egg. The equation representing the preparation of pancakes for this recipe is, there it is. If 2 dozen pancakes are needed for a big family breakfast, the ingredient amounts must be increased proportionally according to the amounts given in the recipe. For example, the number of eggs required to make 24 pancakes is blank. Or there. Balanced chemical equations are used in much the same fashion to determine the amount of one reactant required to react with a given amount of another reactant, or so to yield a given amount of product, and so forth. The coefficients of the balanced equation are used to derive stoichiometric factors that permit computation of the desired quantity. To illustrate this idea, consider the production of ammonia by reaction of hydrogen and nitrogen. This equation shows that ammonia molecules are produced from hydrogen molecules in a 2:3 ratio, and stoichiometric factors may be derived using any amount or number or unit. These stoichiometric factors can be used to compute the number of ammonia molecules produced from a given number of hydrogen molecules, or the number of hydrogen molecules required to produce a given number of ammonia molecules. Similar factors may be derived for any pair of substances in any chemical equation. Can read that. So, numerous variations on the beginning and ending. Computational steps are possible depending on what particular quantities are provided and sought, volumes and concentrations, and so forth. Regardless of the details, all these calculations share a common essential component The use of stoichiometric factors derived from balanced chemical equations. Figure 411 provides a general outline of the various computational steps associated with many reaction stoichiometry calculations. 4.4. Reaction rates. Learning objectives. By the end of this section, you'll be able to explain the concepts of theoretical yield and limiting reactants reagents, derive the theoretical yield for a reaction under specified conditions, calculate the percent yield for a reaction, the relative amounts of reactants and products represented in a balanced chemical equation are often referred to as stoichiometric amounts. All the exercises of the preceding module involve stoichiometric amounts of reactants. For example, when calculating the amount of product generated from a given amount of reactant, it was assumed that any other reactant required were available in stoichiometric amounts or greater. In this module, more realistic situations are considered in which reactants are not present in stoichiometric amounts. Limiting reactant. Consider another food analogy, making grilled cheese sandwiches. 1 slice of cheese plus 2 slices of bread equals 1 sandwich. Stoichiometric amounts of sandwich ingredients for this recipe are bread and cheese slices in 2-to-1 ratio. Provided with 28 slices of bread and 11 slices of cheese, one may prepare 11 sandwiches per the provided recipe, using all the provided cheese and having 6 slices of bread left over. In this scenario, the number of sandwiches prepared has been limited by the number of cheese slices, and the bread slices have been provided in excess. Consider this concept now with regard to a chemical process. The reaction of hydrogen with chlorine to yield hydrogen chloride is H2 plus Cl2 equals 2HCl. The balanced equation shows the hydrogen and chlorine react in a 1-to-1 stoichiometric ratio. If the reactants are provided in any other amounts, one of the reactants will nearly always be entirely consumed, thus limiting the amount of product that may be generated. This substance is the limiting reactant, and the other substance is the excess reactant. Identifying the limiting and excess reactants for a given situation requires computing the molar amounts of each reactant provided and comparing them to the stoichiometric amounts represented in the balanced chemical equation. For example, imagine combining 3 moles of H2 and 2 moles of Cl2. This represents a 3-to-2 ratio of hydrogen to chlorine present for reaction, which is greater than the stoichiometric ratio of 1-to-1. Hydrogen, therefore, is present in excess, and chlorine is the limiting reactant. Reaction of all the provided chlorine will consume 2 moles of the 3 moles of hydrogen provided, leaving 1 mole of hydrogen unreacted. An alternative approach to identifying the limiting reactant involves comparing the amount of product expected for the complete reaction of each reactant. Each reactant amount is used to separately calculate the amount of products that would be formed per the reaction stoichiometry. The reactant yielding the lesser amount of product is the limiting reactant. For the example in the previous paragraph, complete reaction of the hydrogen would yield that stuff. The chlorine will be completely consumed once 4 moles of HCl have been produced. Since enough hydrogen was produced to yield 6 moles of HCl, there will be unreacted hydrogen remaining once this reaction is complete. Chlorine, therefore, is the limiting reactant, and hydrogen is the excess reactant. Percent yield. The amount of a product that may be produced by a reaction under specified conditions, as calculated per the stoichiometry of an appropriate balanced chemical equation, is called the theoretical yield of the reaction. In practice, the amount of product obtained is called the actual yield, and it is often less than the theoretical yield for a number of reasons. Some reactions are inherently inefficient, being accompanied by side reactions that generate other products. Others are by nature incomplete. Consider the partial reactions of weak acids and bases discussed earlier in this chapter. Some products are difficult to collect without some loss, and so less than perfect recovery will produce the actual yield. The extent to which a reaction's theoretical yield is achieved is commonly expressed as its percent yield. Percent yield equals actual yield over theoretical yield times 100. Actual and theoretical yields may be expressed as masses or molar amounts, or any other property, e.g. volume, if the product is a gas. As long as both yields are expressed using the same units, these units will cancel when percent yield is calculated. Or 5, quantitative chemical analysis. Learning objectives. By the end of this section, you'll be able to describe the fundamental aspects of titrations and gravimetric analysis, perform stoichiometric calculations using typical titration and gravimetric data. In the 18th century, the concentration of vinegar samples was determined by noting the amount of potassium carbonate, K2CO3, which had to be added a little at a time before bubbling ceased. The greater the weight of potassium carbonate added to reach the point where the bubbling ended, the more concentrated the vinegar. We now know that the effervescence that occurred during this process was due to the reaction with acetic acid, the compound primarily responsible for the odor and taste of vinegar. Acetic acid reacts with potassium carbonate according to the following reaction. The bubbling was due to the production of carbon dioxide. The test of vinegar with potassium carbonate is one type of quantitative analysis. The determination of amount or concentration of a substance in a sample. In the analysis of vinegar, the concentration of the solute was determined from the amount of reactant that combined with the solute present in a known volume of the solution. In other types of chemical analyses, the amount of a substance present in a sample is determined by measuring the amount of product that results. Titration. Oops. The described approach to measuring vinegar strength was an early version of an analytical technique known as titration analysis. A typical titration analysis involves the use of a burette to make an incremental additions of a solution containing a known concentration of some substance, the titrant, to a sample solution undergoing the substance whose concentration is to be measured, the analyte. The titrant and analyte undergo a chemical reaction of known stoichiometry, and so measuring the volume of titrant solution is required for complete reaction with the analyte. The equivalence point of the titration allows calculation of the analyte concentration. The equivalence point of a titration may be detected visually if a distinct change in the appearance of the sample solution accompanies the completion of the reaction. The halt of bubble formation in the classic vinegar analysis is one such example, though more commonly, special dyes called indicators are added to the sample solutions to impart a change in color or at very near the equivalence point of the titration. Equivalence points may also be detected by measuring some solution property that changes in a predictable way during the course of the titration. Regardless of the approach taken to detect a titration's equivalence point, the volume of titrant actually measured is called the endpoint. Properly designed titration methods typically ensure that the difference between the equivalence and endpoint is negligible. Though any type of chemical reaction may serve as the basis for a titration analysis, the three described in this chapter, precipitation, acid, base, and redox, are most common. Additional details regarding titration analysis are provided in the chapter on acid-base equilibria. This picture. I've always liked titrations. Gravimetric analysis. A gravimetric analysis is one in which a sample is subjected to some treatment that causes a change in the physical state of the analyte that permits its separation from the other components of the sample. Mass measurements of the sample, the isolated analyte, or some other components of the analysis system, used along with the known stoichiometry of the compounds involved, permit calculation of the analyte concentration. Gravimetric methods were the first techniques used for quantitative chemical analysis, and they remain important tools in the modern chemical laboratory. The required change of state in a gravimetric analysis may be achieved by various physical and chemical processes. For example, the moisture, water content of a sample is routinely determined by measuring the mass of a sample before and after it is subjected to a controlled heating process that evaporates the water. Also common are gravimetric techniques in which the analyte is subjected to a precipitation reaction of the sort described earlier in this chapter. The precipitate is typically isolated from the reaction mixture by filtration, carefully dried, and then weighed. The mass of the precipitate may then be used along with relevant stoichiometric relationships to calculate analyte concentration. The elemental composition of hydrocarbons and related compounds may be determined via gravimetric method known as combustion analysis. In a combustion analysis, a weighted sample of the compound is heated to a high temperature under a stream of oxygen gas, resulting in its complete combustion to yield gaseous products of known identities. The complete combustion of hydrocarbons, for example, will yield carbon dioxide and water as the only products. The gaseous combustion products are swept through separate pre-weighed collection devices containing compounds that selectively absorb each product. The mass increases of each device correspond to the mass of the absorbed product and may be used in an appropriate stoichiometric calculation to derive the mass of the relevant element. And that is it. That's chapter 4.